and but we are talking about a different kind of search problem where we are just interested to identify the goal, right? So we are not really interested to know in which path we have achieved the goal, right? And then we have tried to formalize the problem in such a way that we'll be able to come up with algorithms that will be problem independent, right? So we can think about algorithms which does not really depend on the problem that we have in hand. The same algorithm should work for different problems, right? And in this process, we have tried to formalize different problems in the CSP framework. And finally, we stopped at talking about something called concept graph, where we observe that we can represent a constraint satisfaction problem in a form of a graph. And our claim was we'll be using that graph data structure to come up with our own algorithm, right? So to illustrate the concept constraint graph further, so let me take this example, which is a correct arithmetic problem, which I guess you have seen earlier in the other classes. So what I'll do, I'll try to accelerate a bit today. So I'll touch upon different concepts. Maybe I'll not be providing details of those, but for the details, you might need to look at the YouTube video lectures that I have already uploaded, right? And there, I hope that the details are there, but at any point, if you have any doubt, you can just ask on the MS team or you can email me. That's not a problem. So as we know this problem very well, so I'm not going to describe this problem, right? I just would like to give you a very brief overview how to model this as constraint graph, right? So you know the variables. The variables should be this alphabets like hello. Is there any question or any doubt?
Sorry, sir.
Okay. So these alphabets basically are the variables for which we need to find the values. But on top of that, we need to consider that while you are adding two digits, there might be a possibility that we'll be having carries. So in this case, we'll be considering carries in three places. This place, C1, C2, and C3. So these are the possible three places where we can have carries. So our variables would be the unique alphabets that you can find here and the carries, C1, C2, and C3. Right. I'm not going to write it, so you can go back and check the YouTube video lecture. And what are what would be the domains of these variables? The domain should be like one value from 0 to 9. So each of these, apart from C1, C2, C3, will be assuming values to 1, 0 to 9, right? And how should we define the constraints? First constraint that we should define is that the individual alphabets that we are considering here, they should not be assuming same value. So they should be all different, right? So this is the kind of constraint that we are putting. So this constraint graph is a different constraint graph than the constraint graph that we have talked about for the map coloring problem, right? In map coloring problem, we had one binary CSP, right? Because we were having two variables in our scope, right? And the relation between these variables that you have talked about. So that's why that is a binary CSP, and consequently, our constraint graph was a binary constraint graph. But in this case, you know that this is not going to be a binary constraint graph because of the very fact that at least here you can see that there are multiple variables associated. So here you have C1, W, and U. So it is not going to be a case of binary constraint graph, right? Now let us try to define the constraints. So C1 can assume value from either 0, 1. Now this is where we are talking about that this is going beyond binary constraint. Here, this node is considering the fact that we have kind of contribution from this O, we just add O plus O, and as a result, what we get R and a carry, right? C1. And we know that the addition of these should be R. So addition of these two would be R plus 10 multiply C1. So the normal way in which we perform addition operation. And similarly, you can define the constraints for the other variables. And these are the set of constraints. And that's how we can define this script arithmetic problem in a CSP formalism. And this is the corresponding constraint graph for this particular problem, right? So again, you know that the graph can be different for different problems, right? Now, let's say we have converted a problem into a graph structure like this, but what is the big deal? So the big deal is that we can design CSP solvers in such a way that it can prune a very large portion of the search space. And if we can do that, we can see that we can have a very efficient solution. And that is the kind of hope that we have with us, right? Now let us talk about different variations of CSP. So the first variation I'd like to talk about is with respect to the variables, right? So the variation can be with respect to the variables, or it can be with respect to the say type of constraints that we are dealing with, right? Now, the first kind of variation that I'd like to talk about is where the CSP considers discrete variables. So I guess we have taken examples of such cases. Now let me try to divide it into more finer categories. So the one category is that discrete variables, they belong to finite domains, right? So for example, we were assigning say 0, 1, 2, 4 to 9 for the crypt arithmetic problem. So there, that is a case of discrete variable, right? Now, if you have n such variables and the size of the domain is D and the domain is discrete, right? So how many complete assignments we'll get? Basically, that will be order of D to the power n complete assignments. And specific example of this case is the Boolean CSP, which we have already talked about. And of course, there is a specific problem which we call a satisfiability problem. And that is the problem we will be talking about in the next module. So basically here you are given with a knowledge base in form of like Boolean formulas, right? And we know that using propositional logic or first order logic, and we can design knowledge base. So there we will like to ask whether the knowledge base is satisfiable or not, the knowledge base is consistent or not. So that is what we call as the satisfiability problem. And 3SAT is a very specific instance of that satisfiability problem. So we'll talk about this later. So of course, as you see that we have got n variables and this number of complete assignments. In the worst case, you can have exponential order of size of the problem and as well as size the runtime, right? And of course, we will try to talk about the solvers, which will try to prune this search space to come up with solutions very fast and effectively. The second kind of problem that I like to talk about is the case of infinite domains. So infinite domain again can be integers, it can be string. So one such example could be like job scheduling. So for example, you are running a factory and there are certain jobs that are to be done. And the jobs are described by specifying the start and end days, right? So basically duration. So you have jobs and the jobs have got certain durations, right? And what you need to do, you need to come up with a schedule where you can schedule the job in such a way that you specify the start date or time of the job and end date or time of the job, right? So you can see that this duration can take any value. It can take say 5 minutes, it can say take 30 days, it can say take 1 year. So you do not have any limit on this duration. So as a result, you can think this domain to be the domain of the variable to be infinite. Now, in order to capture this kind of problems, we need to have a constraint language which will be looking like this. So for example, we want that the job two should not start after 10 days after starting job one, right? So that is the kind of constraint that we are putting. And this is one thing that I like to just mention that I'm not going to prove this. If you have linear constraints of this form, then the CSP is solvable. But if you have non-linear constraints, the CSP, you do not have a general algorithm to solve that. You have to try out different heuristics, maybe domain-specific heuristics to solve this problem, right? Now, the other case is a continuous variable, right? So basically your values of the variable, they belong to a continuous domain. So we have talked about an application of CSP like Hubble Space Telescope, where the telescope has to come up with a schedule of observations. And this schedule is basically coming from a continuous domain. So whatever time value you assign for starting a job, starting an observation, that can be any time value. It may be, say, 5:55 AM, or it can be anything. So it is not discrete. So that is one example. And this kind of problem can be solved or modeled using linear programming problems. Now, there are certain variations if we consider the kind of constraints that we are handling in our problem. So first kind of constraint, which is very simple to consider, is unary constraint, and that concerns assignment of single variable, and it will not really concern assignment of the other variable. So for example, I'm very fixated with the idea that I'll never paint essay with green. So that is kind of constraint that we are putting, and this constraint involves only one variable. And that's why it's called the problem that involves unary constraints. The problem again can involve binary constraints, as we have talked about earlier, and it takes care of a pair of variable in its scope. One example of this sort would be SA not equal to WA. Or you might be having higher order constraints that involve three or more variables. And we have seen an example of this kind of problem, like in cryptographic arithmetic problem. And so whatever kind of constraints that you have talked about, they are called hard constraints. So whatever solutions you come up with, they should always satisfy these set of hard constraints. But there might be real world applications where not only you impose hard constraint, but you also prefer some solution over other solution. And you put the preferences in the form of soft constraints. Right? For example, while you are doing this timetabling exercise, so Professor A might say that I will prefer to have classes in the second half. But you see that if you satisfy Professor A's request, that solution would be better than you don't satisfy Professor A's request, but Professor A should not mind if this has been scheduled in the first half. So basically, while we are talking about incorporating preferences in the form of soft constraints, we are solving two problems together. One is optimization, other is CSP, right? So we are satisfying some constraints, and also we are optimizing our solution by looking at how many such soft constraints I have satisfied. So as many as soft constraints I have satisfied, the quality of the solution will be better, right? Now with this, let us go to the solvers. So first I'll describe the basic solvers, then I'll be going to the efficient solvers. Now these basic solvers will be designing in a very principled way, right? So we'll start with the first principle, and we know that what is a search problem. So let us try to model CSP as a search problem. Now again, what we need to specify a search problem. So can anyone from you tell me what are the things that I need to specify?
Sir, an initial state.
Yeah, initial state. Any what are the other things?
Then I need the next successor,
Right.
and then I need to do a goal check.
Okay, good. Thank you. So let us see whether we can frame CSP in that structure or not. So what would be our initial state? What do you think? Anyone? So given the formal description of the CSP problem, so tell me what should be the initial state? You should be in a position to answer this.
So no assignment to any variable, empty
Exactly. So
assignment.
exactly. So for that, we need to know what is the state. State is basically the set of variables that we are interested in. And if we do not have any assignment, we are starting with an empty assignment, and that is really the initial state. We start with an initial state. Now, what is the successor function? Successor function is basically will be we are assigning one value to a variable, right? We are choosing a variable and assigning one value. If we do that, we come up with a new assignment, right? So basically, we take an unassigned variable and we assign a value without any conflict with respect to the other previously assigned variables. And of course, we need to think about the constraints that we have already discussed, right? Or framed for this particular problem, right? And what would be the goal test? We know that, right? So it should be a consistent and complete solution, right? So whether you need to understand or check whether the current assignment is complete. And of course, the way we are designing the successor function, we are saying that there should be no conflict if we arrive at the complete solution. So that will be our goal state. And the path cost would be if we just assign a constant cost for every step, that will be our path cost. But we are not really interested to know what it be the path cost. We'll just try to see whether our goal is satisfied or not, right? So basically, what we are talking about is an incremental formulation. We start with an empty assignment and incrementally assign the unassigned values, right? And one particular property that CSP will always hold, that every solution that we think about will appear at depth n if we have a problem which involves n variable. And that is well understood, right? So as a goal, I have to assign every n variable, and the way we are expanding our search space, we are at every step we are assigning one value, and as we go to nth depth, so that means we are assigning n variables. So this is how we are doing a kind of incremental formulation. So if we have a situation like this, we have our search tree that extends up to n depth. So now what is the kind of takeaway from this? So basically, if you think about general search problem, your search space, you do not have a bound over the search space. You cannot really tell what would be the complete size of that set space. Well, you can have an estimate, but you don't know where the solution would be, right? It's the solution can be in the first depth, it can be in the second depth, or it can be in any arbitrary depth, right? But here the beauty is that a solution always appears in the nth depth, right? And that brings us uh, to apply the depth first search algorithms for CSPs. And it is a matter of fact, whatever algorithm we'll be talking about in CSP, they are all devised over depth first search formulation, right? Now, before going to depth first search, let us try to see why we should not use BFS, right? So if we use BFS, what will happen? So we start with an empty assignment, right? Now, after we have started with an empty assignment in the next step, in BFS, what we'll be doing, what we will have, we'll be having multiple assignments where each of these assignments will be having one variable assigned to it, right? And in the next step, each again will be expanded, and each assignment in this step will be having two variables assigned to it. And this is how we will be going to the nth depth where we have all the variables, all the n variables that are assigned in this depth, right? Now, how are you exploring the search space? You are going this way. You're going this way. And basically, what you are doing, you are really guaranteed to perform as much as work possible, right? So you are expanding all the, you are exporting all the assignments in this process. And you know, this should not really be a good strategy. On the contrary, what DFS is doing is starting with an empty assignment, going to the second 2 variable assignment, 3 variable assignment, and it is going really fast to a complete assignment, right? So it might so happen if we take into account this mm, this graph coloring problem or the the map coloring problem in one uh, solution, you have all rates, but you see at this point, you know, that is a conflict with your goal. Now you can, what you can do, you can backtrack here and then you reassign one value, say R B. And that is also a conflict. You go to this, you change the values. That's how you'll be doing here. It's better than BFS because you know you are going to the complete assignment very fast and you are expected to fail fast if you are doing this kind of DFS strategy, right? But again, you see this DFS is also not a good choice because in the worst case, I have to come to the last step. This is the worst case, right? So if we try to do a close analysis of this, so how really we can improve on this? Any idea? How we can improve on this? Anyone?
Sir, like when we generate a successor and
Yes.
like we are doing the assignment right now
Mm-hmm.
independent of whatever other variables are having as their value.
Mm-hmm.
So now if we check, like let's say I have reached a depth L which is less than n.
Okay.
So if like I'm in the middle of finding the solution, so if I
Mm-hmm.
find that my next successor is not satisfying the constraint, I will go
Mm-hmm.
back to my parent node and I will
Mm-hmm.
not like explore that branch anymore.
Good. So basically, what we will try to, let us observe what we are doing. We made several mistakes in between. So in the first case here, I have assigned 2 rates together. Now, even though we see this is a conflict, I keep on expanding this. So this is not necessary. We can prune the search here. We just discard this part, right? So whenever we have a broken constraint, we backtrack, right? So let us have a quick look at how this BFS, or no, I'll not show BFS, I'll show DFS, how DFS kind of algorithm works in this map coloring problem. So just let me know whether you can see my browser. Is it visible?
Yes, sir.
Okay, good. So here, this is a kind of demo that has been developed by Abhishek Gupta from UC Berkeley. So here you can play with this map coloring problem. So this is a kind of general graph you can see, and you can kind of see, visualize the steps of the algorithms that we are going to talk about. So first we'll go with naive search, which is basically DFS. And we are taking a simple graph, but also we can take a complex graph. So for this, I'll take this simple graph. and we'll be doing naive search. So let us not talk about ordering, filtering for now, because we'll be talking about this later. Now, so let us start playing. So in the first place, this will be assigned a value. So the colors are red, green, and blue, as we have talked about earlier. So it has been assigned blue, right? Next, it will be assigned blue, 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 blue. Now we have a conflict here, right? So after, now we are doing very naive DFS here. After we have done all the assignments, then we check for the goal, and our goal is not satisfied. There is a conflict, so we have to revisit this, right? So you have to try out different value. So let us try out red. Is it satisfied? No, because there are other conflicts. So this does not work. But this algorithm does not know that this conflict is not due to the new assignment red on this, but for the other assignments. But it explode the other values here unnecessarily. So green does also does not give you a satisfaction. Then you go back and change this. Now you see it will keep on doing this. So you can say play it, say 1000 speed up, and maybe you see it is not converging. Even I have running. I'm trying to run this for in a very faster manner. So let us not go into this. This is not promising, right? Let's talk about something that is good. So that brings us to the case that Kshitij has just mentioned, that why don't we stop while the constraint is violated? So the kind of key sentence for backtracking search is do not proceed down if the constraint is violated. That's it. And so you can think of this backtracking search is a kind of baseline search technique for the CSP algorithm category, if we talk about complete algorithms. And you can think this to be a kind of uninformed algorithm for CSP. We have talked about uninformed algorithms for search, right? So there we do not use any heuristics. So when we have uninformed algorithm, that means we do not use H, right? So here also we do not use any heuristics in simple backtracking search. And these we have got many observations here. So one observation is that the kind of way we are assigning the values that are independent, right? So I can choose one green value, I can choose a red value, I can choose other value, right? And also the order in which we are choosing the variable, that will not affect the outcome. So for example, if we have these two pairs, like we are assigning SA to red to SA and then green to Q, first we assign SA. So this is the first assignment we have done, and this is the second assignment. And this is as same as we have a first assignment, we have green assigned to Q and red assigned to S. These two are equivalent. So that tells us that CSP is commutative. So we can also prune in that respect. If we somehow take care of this order, like if we have this order that has been explored earlier, we really do not need to explore this order or this path, right? So this is another kind of optimization that we can do, right? And of course, I have talked about this independence property. So whenever we are generating a successor, we just consider a single assignment to a single variable, right? So assignment might give you a conflict, but while we are assigning, that is independent, right? And this we have already talked about, that we are having 2 to the power n unique leaves, right? And of course, as you have mentioned, that we will be checking the constraint as we are going. So after assignment, every assignment we will be checking the constraint. Now, what kind of limitation does it have with respect to the DFS algorithm? So if we just compare DFS with this, I'll not say limitation. So you're losing out something. So what is the thing that we are losing out? After every assignment, we are checking a constant. So that will add extra bit of work. But we will not really mind this, because for this extra bit of work, we will be able to prune a larger part of the search space, right? But this is one thing that we need to do a kind of checking, right? So let us give you a very, so I'll say bird's eye view of this backtracking search. Then we can go the formal algorithm. So there are basically three steps. First is the expand step. And in the expand step, what do? You pick up a single variable that you will like to expand. And for this particular chosen variable, you iterate over the domain values that the variable has, right? So what we are really talking about. So we have an empty assignment. We started with an empty assignment. And we have chosen this variable to expand. So, and this is the iterate step. We are iterating over all the values that this variable can have. So basically red, green, and blue. Now then, we will be processing children. So the children will be based on the values. So we will be processing this, right? Now, if we process this, we will pick up the next value to be this. And we can assign again three values. Now, then we'll be checking whether there is a conflict or not, right? Now, for the first case, you have a conflict, so you don't go with this, but here we do not have a conflict. Now, as this is not having a conflict, so this is a potential solution, we'll be expanding this. And you see, this is a kind of conflicting solution. This is a kind of conflicting assignment. Then we'll be proceed with this. And you see, this is a kind of very first principle way to go for this algorithm. And we know that intuitively it should work, right? So this is the concrete algorithm. I don't think I'll be explaining it here. I have explained it in the video lecture. And again, I'm just coding it from what we have just talked about in the earlier slide, right? And basically here, this backtracking search is a combination of three things. We do our DFS. We do a variable ordering. What kind of variable ordering we should talk about? Basically, if there is a commutative case. So this is handling the commutative case. We really can discard the other alternatives, right? And whenever we have a conflict, then we say a flag of failure and we just backtrack, right? This is basically the algorithm. So let us have a quick demo on this to see whether it works better than the naive search. Right? So for that, we will be selecting backtracking and we will not be selecting any of this, right? So let us try to play. So you see, we have converged to the solution pretty fast, right? So because of the very fact, whenever we are having a conflicting assignment, we are discarding that and checking for other children, right? Now let us try to make this baseline backtracking algorithm more efficient. So how do we do that? So basically we can look at different things. So first thing is that we can tune two things. One is whenever, so let us see what are the kind of choices that we are making in the backtracking search. One choice is we are choosing a variable for expansion. So that is one thing that we are doing. And what is the second thing that we are doing? For a chosen variable, we choose a value. Now, this we are expanding or choosing in an arbitrary order, right? So our question is whether if we order the variables when we are choosing the variable and if we order the values, whenever we are choosing a value for the chosen variable, have got any implication on the runtime of the backtracking search algorithm. So this is one thing that we'll be exploring, and this will give us a heuristic. Now, I promised with something in the very beginning that whatever method, whatever heuristics that we'll be talking about, they are domain independent. So do you think whatever heuristics that will concern this ordering intuition would be domain independent? So can we design, first of all? What do you think? Rohit? Hello, Rohit, are you there? Well, either you are not there or you have some doubts. So if you have some doubt, please flag. Okay, Apurv?
Yes, I'm there.
Yeah. So what I am asking, so our original objective was to design heuristics that are domain independent. So do you think these ordering heuristics can be implemented in a domain independent manner? So let me first ask, have I talked about anything specific to any problem here while I was talking about this ordering? So this variable ordering will be applicable for any problem. The value ordering will be applicable for any problem, right? So basically, we are going towards a strategy for designing heuristics that are domain independent. So we can really do that, right? So basically what we are talking about, let's say we have selected this Western Australia first. So this was the variable that was assigned by some means. So the next question is which variable to assign. So we can choose one, but whatever we choose, then we ask what value to choose, right? So other heuristics or other question we can ask to make backtracking more efficient, that whether we can detect failures early, and what is the implication if we can do that? We can prune the search space in a larger way. And let me remind you that we are doing DFS. So if we can detect failure early in the earlier depths, so we really do not need to explore the remaining part of that depth, right? Or that path. So we'll be talking about this, of course. And the third thing that we like to check whether the structure of the problem can be exploited or not. And here again, though it looks like to be a problem specific specification, so it is not a problem specific specification. So basically, this problem is the structure of the CSP problem. And what is the structure of the CSP problem? We have talked about the structure to be a binary CSP graph here that we drawn, right? And for crypt arithmetic, the graph was kind of different. So the question is, can we exploit the structure of this constraint graph? So these are the three key questions that will give us very nice and elegant heuristics to solve the problems at our hand. So let me go with first the filtering idea, right? So basically, whenever we are assigning a value to a variable, let us take a stock of the unassigned variables. And if we see that some of the options for the unassigned variables are not going with the assignment of the current the value of the current variable, then we will filter them out. So basically the core idea is filter out the bad options, right? And this informal term is what we call as forward checking. So basically we are assigning, while we have assigned a value to a variable, we check in the constant graph in a forward manner to see whether other variables, they do have any effect of these assignments. And as an effect, we will strike off the bad options. So let us try to visualize what I'm trying to say. So again, we start with an empty assignment. And for this initial state, we know that all three values are possible for all three variables, right? And in the next step, what we have done, we have assigned red to the first variable. So our WA become all red. And as I have painted WA with red, what are the interacting variables? NT is an interacting variable. So NT should not be having red. So I strike off red from here only to have this green and blue option. Q does not interact with WA. So that means I can have all the options intact. NSW does not interact with WA, and V does not interact with WA. So all the values are as it is. But SA interacts with WA, so that means red should be stricken off from here, right? So let's say in the next step, we assign green to say Q. So after we have assigned green to Q, so that means NT is interacting with Q. I should not have green here, right? I should not have green in NSW. I should not have green in SA, but all the values in V are intact. And finally, let us assign, say, blue to SA. Sorry, blue to Victoria. Now, if we assign blue to Victoria, now you see that I do not have any option for AC. And we can detect a failure. So this detection is a bit early. So this detection of failure is early. Right. And this particular heuristics is called the forward checking heuristic. So let us try to see whether we are having any kind of gain here or not. So basically for that, we will be checking this filtering. So we'll be using this forward checking. Now you can see that we have got all the options because we will be playing with the value. So let us try to see how this algorithm works, right? So in the first case, first node will be assigned a value blue. And as soon as I assign a value blue here, so this node will not be having blue value in its repository, and this node will not also be having blue, right? Next, we can choose any one of this. So let us choose this to be red. And as soon as I choose this to be red, I do not have the blue and the red option here. I have only green option. And subsequently, the other nodes, the options for the other nodes, they have got changed. Now we can assign a blue value here because that is valid. As we do that, we have got limitation options in the connected nodes. We can assign red here. And if we assign red here, I can safely assign, say, green here. Now, if we assign green here, I do not have anything to assign. Now I have a failure here. So as I have a failure here, I'll be backtracking. Now I have to come up with another option than green, but this node was having only option to be green. So that means I have to backtrack here, right? Now you will be seeing that we'll be backtracking here, right? So we have chosen red earlier. Now we can choose green here. Now, as I choose green here, I do not have any option to be placed here because I have all the red, green, and blues have been used in the neighboring nodes. So you see, I have failures at very early stage, in very early depth value, right? And that's what the advantage that we get if we use these filtering heuristics, right? Now, here we have talked about checking the assignment locally. So I'll just check whether my assignment of my variable, whether that has got implication of the variables that are neighboring to me, right? But it might so happen that when you assign a value to one variable and that has got an implication to the other variable, that in turn might have implication in the other connected variable, which is not directly connected to the first variable. So basically, whatever decision that we are making in a node, respecting the constraint, that may percolate to the other part of the network. So let us try to see a situation here. So I think we are taking the same example. And in this scenario, what we have got this red to be assigned to WA and Q to be assigned to green to be assigned to Q. And this is where we are standing, right? Now let us try to think of so we have this option, this condition here. So this NT and SA, they have to be assigned both the same value blue. I have no other option. And that is clearly a constraint violation that I'll be having. But this forward checking will not see that. The forward checking will only see that after it has assigned a value blue here. So you see the problem. So even though I know at this point that I do not have a valid assignment going forward, still I'm going forward with my assignment, with this filtering. Because my assignments, the effect of my assignment, current assignment is not propagating in the other part of the network. And that will, so we want to detect it earlier, and the way to detect is to propagate the constraint from one part of the network to the other part of the network. So basically here we will be checking different kind of interaction between the unassigned variables, right? So let us try to make it bit concrete. So if we want to make it bit concrete, we'll define the interaction between a pair of variables, right? And whenever we are considering the interaction between a pair of variables, so that means we are checking the constraint that is placed on the edge that connects to variable. So listen to me carefully at this point. So you have got two variables, x1 and x2, right? And while we are trying to see whether they have mutually valid assignment or not, we are just checking whether the constraint that is imposed by that particular arc or edge is satisfying or consistent or not. And that's why this is called arc consistency, right? So let us try to define what do we mean by arc consistency. So we say that an arc, so this arc is always directed. So you have two variables x and y. We are probing this arc whether this is consistent or not, right? Now we will say that this arc is consistent when, let me tell you the situation first. So the situation is I have frozen the set of assignments that are valid at this point for y. So this part I have frozen. So I'll not be modifying this. But what I can do, I can modify this. Whatever options I have here, I can modify this. So what is the modification we will be doing? Only modification we will be doing is to delete one option, one value from here, value option. And which value option will be deleting? For which I do not have at least one satisfying assignment in y. So it might so happen that while you have assigned a value here, it is conflicting with this assignment, but it is fine with this. So that means I have at least one pair of assignments for which this arc is, the constraint that is imposed on this arc is consistent, right? So if that is so, then I'll say that this value is consistent, I'll not be removing this. But if this so happens that for both of these y values, I do not have a consistent assignment for this particular value, then we say we have to delete this because this is not going with this or this. So I have to delete this. Right. Now, if we have a rule like this, X and Y, so let me define two things. One is head and other is the tail. So this X is what we call as tail and Y is what we call as head. So whenever we will be deleting a particular element from to make this pair consistent, we will always delete from tail. So this is one thing that you should understand, and because of the very fact or reasoning that I have just mentioned here. So always delete from the tail, right? So now with this, let us try to define what do we mean by arc consistency. So a given arc X to Y is consistent if all the values that X can assume, for all the values, there exists at least one value in Y, which is in head, which can be assigned without violating any constraint. So that is my definition of arc consistency, right? So let us go with some example. First of all, when the things are not consistent, and in order to make an arc consistent, what we need to do. So let us try to first check the arc from V to NSW, right? Now you might say or debate that we have considered the constraint graph to be undirected. So it did not have any direction there. But here we are talking about direction, right? So do you have such question in mind? I hope that you will be raising this. So basically, here the directionality is there because you see, I am fixing one particular node, values of one particular node, and changing the other particular values of the other node, right? So I can do the similar in the flipped version of the edge. So I can do the same for Y to X. So basically what we are doing, the constraint graph, though that is undirected, we can make that to be directed by. So if we have a kind of situation like this, undirected situation like this, I can have this and I can have this also, right? So while I'm checking the arcs of the CSP, I have to check every such edges or arc if they're consistent or not, right? So let me now check whether this assignment or this arc from V to NSW is consistent or not. So what do you think? Would it be consistent? So how do we check? So what is our X and what is our Y? Our X is V and Y is NSW, right? So we have fixed NSW and we need to check whether any assignment of V will violate. So let us check red. Is it violating any constraint? So if I assign red here, so V and NSW, V is this, and NSW is this. So they are neighbors. So they should not have same color, right? So if I assign red here, I can simply assign one of green or blue. So this is fine. So this red is fine. If I assign green here, again, that is fine. You know that. And the similar thing is true for these values. So that means this V2 NSW is consistent, right? Now let us check, let's say for say SA2 NSW. So for the similar reason, so for the similar, by going with the similar logic with respect to the previous example or previous case, this is also consistent, right? So V2 NSW is consistent. SA2 NSW is consistent, right? Now let us check the other direction from say NSW to SA. So I told you that these two arcs are not equivalent, and we'll just demonstrate here. So I'm now checking NSW to SA. So that means what we have done, we have fixed SA, will not be changing SA, but we will be we'll be trying to change values from here, right? So if we have assigned, say, red here, right? If we have assigned red here, so SA cannot have red, right? So I do not have this here. Right? Now, if I assign green here, so we'll be checking each of these here, right? So if I assign red here, so I have option to be this blue and green, they are safe, right? And if you're assigning say green here, I have again the safe option to be blue. And if I assign blue here, I have the same safe option to be green. So this is becoming to be consistent. Something is wrong here. So yeah, I think I will resume this part later. So I guess I have drawn this in a wrong way. So I need to revise this maybe. So I think I will resume this in the next class. Thank you. So apart from this, whatever you have discussed, any doubt on that? I'll review this. Don't worry about this. There is something wrong here in this example. I'll check this out later. Any other questions? Well, so if that not so, we'll just stop for today.